All right, we are back again to look at coordinates, coordinate vectors relative to a basis. So let's say you have a basis with C basis vectors. It's a basis for some subspace U of Rn. Maybe U is like a plane in R3, or maybe U is like a 7-dimensional hyperplane in R12. Could be anything like that. Or maybe U is just like a line through the origin in R2. Or maybe U is Rn itself, right? That's also a subspace of Rn. Anyways, if you have any vector in U, if we can write that y as this linear combination of the basis vectors where the weights are x1 through xc, then we say the vector that has those entries in it is called the b coordinate vector of y, and you write it like this. Sometimes I call it the coordinates of y relative to b. So this is a thing that a lot of people get mixed up. People get mixed up between like which one is actually y versus which one is the y coordinates relative to b. Causes much confusion in my experience teaching linear algebra. My advice is, if you're not sure whether you're supposed to be finding this thing or which one is which, my advice is come back and read this definition, because for some reason it throws people off. So come back to the definition when you need it. Okay, let's look at example 6. So we have a basis of two vectors, 3, 1, and -4, 2. That is a basis of R2. And we can see that on the graph. Here's 3, 1. Here's -4, 2. And yeah, they are linearly independent. Like neither of them is on the span of the other one. If it was like B2's right here, then it would not be a basis. And also we can see that any old vector in R2, there's a way to get there doing some linear combination of B1 and B2. So yeah, it's a basis. Let's use the graph to find y if the b coordinates of y are 1, 2. Okay, so let's remember, what does it mean to say the b coordinates of y are 1, 2? Does that mean y is right here because that's 1 and 2? No. Let's check the definition. We have the b coordinates of y are the coefficients of the basis vectors. That gets you y. Oh, okay. So according to that, that means if you do 1 times b1 plus 2 times b2, you should get y. And I know we could just do it with the numbers here, but it's good to get a visual understanding for what this looks like. So let's look at the graph. Here is 1b1 right here, 1b1. 2b2 means we're going to take a vector that's twice as long as b2, which looks like that. So connect them tip to tail like that, and what you get is y. And that y is the point -5, 5. And you can check that using the numbers if you want. All right, let's see. This says find the b coordinates of -3, -1. So this is saying we want to know the coordinates of something. We want to know what is the x1 and the x2 that gives you -3, -1. So the thing inside the brackets, that's the y. That's the result we want to get. -3, -1. And the coordinates are going to be these coefficients. So that means the actual point we're talking about is -3, -1. So here's -3, here's -1. There's the point -3, -1. So what do we do with the b basis vectors in order to get to this point? Well, it looks like you could just do negative b1, right? -1 times b1, and you'll land right there. And then 0 b2, because we don't want to go in the other direction at all. And oh yeah, that is exactly the opposite of b1, so you can see it there. So that means the coordinates of this point relative to the basis b is -1, 0. So again with this one, if this is saying find the b coordinates of 10, 0. So in other words, what are the coefficients of b1 and b2 that make you get 10, 0 as that linear combination? Well, let's find 10, 0 here. 2, 4, 6, 8, 10. And we get there, how do we get there? By doing multiples of b1 and b2. It looks like you could do 2b1, and then from there follow this grid line by adding -b2 to get to that point. So 2b1 and -1b2 looks like you would get to 10, 0. So you notice what we're doing here is like we're using like the coordinates are coordinates on a b1, b2 grid. So it's like we have the origin in the same place. Those have to line up. This is like 1 on the b1 axis, 2, 3, and then here's the b2 axis with 0, 1, and -1, and so on. Okay, to find the b coordinates of 7, -1, that's part D. That means the point is 7, -1 right here. So what are the coordinates relative to the b1, b2 axis? Well, it's like 1, b1, -1, b2, right? So the coordinates are 1 and -1. What are the b coordinates of b1? Oh, well, here's b1 itself. How do you get to b1 along these grids? Well, you just do 1 times b1 plus 0 b2. So this is just going to be 1, 0. And of course, if you want to write any of these in vector format, that's the same thing. All right, sounds good. Now, there's nothing really new here. This is really a different way of looking at the same kinds of things you're doing. Like if you're finding coordinates relative to a basis, it's the same idea as like solving an equation, like finding out what are the coefficients that get you this result. But it gives you maybe an intuitive way of looking at things. Like you can look at this alternate grid and say that like, oh, when we solve an equation to find like what are the coefficients of the basis vectors, you're really figuring out what the coordinates on this alternate grid are. And that can help you understand things a little better, especially when we get to stuff later in like chapter 5. And it is going to be really important in chapter 7. Okay, let's look at a couple theorems here. I think these are not too controversial theorems. You do need them to prove things later on. But I think they're pretty intuitive. So, and the proofs actually are not too bad. So you're going to have the proof as homework assignment to fill in the gaps that are missing in the proof. So I'm not going to go over the proof right now, but let's just look at it and see why it seems reasonable. It says, suppose that B is a basis for a subspace U of Rn. Then for every y in U, there is only one B coordinate of y vector. Now, just as an example to get a feeling for why this works, like if I take a point over here, is there more than one way to get here along this grid? I mean, I guess like you could say, oh, I could go backwards and like around the circle or something and then get there, but you're just adding up multiple copies of B1 and some negative ones are going to cancel out. Like, for example, what I mean is, I think what I just traced out was doing 3B1 plus B2 minus B1 minus B2 plus B1 and plus B2. Whoops. And that's all going to simplify to make, if you combine the like terms, it's just 3B1 plus B2. So there's really only one coordinate vector of 5, 5 relative to this basis, and it is 3, 1. Okay, so yeah, there's really only one coordinate vector for each. And that has to do with the fact that it is a linearly independent set. So that's my hand-wavy justification for that. I'll let you prove it formally for the homework. Let's look at theorem 1.5. Removing dependent vectors doesn't change the span. So if you have a list of vectors, and I'm saying a list because it might not be a basis, it might be linearly dependent, and U is the subspace that is the span of those vectors. If one of the vectors, A sub j, is a linear combination of the other ones, well, that means the set is a dependent list of vectors, then removing that vector from the list doesn't change the span. In other words, the span that you had before is the same as the span of the vectors without aj in it. Like we have aj minus 1 and aj plus 1, but we lost aj. That's okay, because whatever linear combinations you were making with aj, well, aj was a linear combination of the other vectors, so you can still make that same linear combination with the other vectors too. So that's my hand-wavy explanation for that one. Now these theorems are needed to actually prove the theorems we're going to look at next, but we'll do that in another video.